It's genuinely impressive, isn't it? How fast AI is getting better at understanding images.
Oh, definitely. I mean, not long ago, getting a computer to really see meant mountains of human-labeled data.
Exactly. Piles and piles of pictures someone had to look at and tag. But things are changing fast.
They really are.
Yeah.
And that brings us right to the heart of this deep dive, actually.
Yeah.
This new way AI is learning to see images without all that human labeling. Well, it's pretty revolutionary.
Right. So we're digging into some really cool research that a listener pointed us to, 2 key papers.
Yeah, the first one introduces D-Level, that's self-supervised vision transformers with no labels.
Dino, okay. And the second?
That's Dino V2. It looks at the sort of surprising abilities that pop up when you scale these self-supervised models.
Gotcha. And the listener, they're basically looking to get a quick handle on why these are such a big deal for AI vision, right?
That's the idea. Understand the significance of these leaps forward.
Okay, mission set then. Let's unpack how this self-supervised learning actually works and, why it matters so much. Okay, let's dive in.
So traditionally, computer vision.
Yeah.
It absolutely relied on these massive, massive data sets. Think millions of pictures.
Your people had to sit there and draw boxes around everything. Cars, people, cats.
Precisely. Painstakingly identifying and categorizing object after object. Just imagine the scale of that.
Yeah, it sounds like a huge bottleneck. Just the time, the cost. It must really limit how much these models can learn, no?
Absolutely. A major bottleneck. And that's where self-supervised learning, SSL, comes in. It's a totally different mindset.
Okay, different how?
Well, instead of needing those external labels, SSL lets the AI learn from the inherent structure within the images themselves, from the raw data.
Ah, okay. It's sort of like how language models learn just by reading tons and tons of text. They figure out grammar and meaning without explicit lessons.
That's a really good analogy, actually.
Sure.
Yes. Dino takes that core idea and applies it to images using vision transformers or ViTs.
ViTs, right. We hear a lot about those. They handle images differently than older methods, don't they? How do they see?
Yeah, they break the image down. Imagine dividing it into a grid, like a mosaic, of little patches.
Patches, okay.
The original Dino paper looked at sizes like 16 by 16 pixels, but they found something important. Using smaller patches, like 8 by 8, actually helped the model learn better, richer visual features.
Interesting. Finer details matter. So, you break the image into patches. Then what? How does Dino learn without labels telling it what's what?
It uses this clever setup. 2 networks, a student and a teacher.
Student and teacher, like an apprentice model.
Sort of, yeah. And the teacher network. Its updates are based on the student's progress, but smoothed out using something called a momentum encoder.
Momentum encoder, so the teacher learns more gradually.
Exactly.
Yeah.
It provides a more stable target, a more consistent signal for the student to learn from. Keeps things from jumping around too much.
Okay, that makes sense. Stability is key. What else?
Another really crucial piece is multi-cropped augmentation.
Multi-crop. Sounds like you're showing at different parts of the picture.
Pretty much. The model sees the same image, but cropped in different ways. Maybe a couple of large zoomed-in views, and then several smaller ones showing more context.
Ah, so it has to learn what's fundamentally the same across all those different views.
Precisely. It forces the model to build representations that are robust to changes in viewpoint or scale. And the paper really stressed how vital this was, especially for getting good results with a simple k-nearest neighbors classifier, a KNN.
Okay, seeing things from multiple angles helps it generalize. Makes intuitive sense. So how does it actually learn? What's the signal?
Well, the core learning mechanism in Dino is actually pretty straightforward. It uses a loss function.
Right, the thing that tells the model if it's doing well or not.
Exactly. And here, the student network basically tries to predict the output of the teacher network for those different crops of the same image. It uses cross-entropy loss to measure how well its predictions match the teacher's.
So a student tries to mimic the teacher's view of these different crops. Simple, but sounds effective. But wait, how do you stop it from just outputting the same thing for every single image? Collapsing.
Ah, yeah, collapse is a huge problem in SSL. Dino has a neat trick. Centering and sharpening the teacher's output.
Centering and sharpening.
Yeah. Centering helps prevent that collapse into a uniform output.
Yeah.
And sharpening, which is controlled by a temperature parameter, makes the teacher's predictions a bit more distinct. more confident maybe. It gives a student a clearer signal to aim for.
Oh, okay. So those two things work together to keep the learning meaningful and diverse. You also mentioned Dino didn't lean heavily on some other common SSL tricks.
That's right. Things like separate predictor heads or complex normalization layers or even the contrastive losses you see in other methods. The Dino researchers found they didn't add much extra benefit for stability or performance in their specific setup.
Interesting. A bit of simplification there. So, okay, you train it like this, no labels. How well does it actually understand images? What were the results?
Honestly, pretty stunning. The paper showed Dino hitting 78.3% top 1 accuracy on ImageNet.
On ImageNet, the big benchmark.
The very same. And that was using just a basic KNN classifier with no fine-tuning and no extra augmentation during the test, just the raw features learned from unlabeled data.
Wow. Okay, 78.3% with just KNN. That's really good. Almost human level on some tasks, right?
It really signals a major shift. And it got even better when they used a standard linear classifier on top of the features.
So a simple trainable layer.
Exactly. With a VT base model and those smaller 8x8 patches, it hit 80.1% top 1 accuracy on ImageNet.
80.1%. That's seriously impressive for self-supervised back then. And did it only work with ViTs?
Nope, that was another cool finding. It worked well with traditional convolutional networks too, like ResNet 50. It was competitive with the top SSL methods for convents at the time.
So versatile across architectures. What about efficiency? Training these big models takes a lot of compute, right?
Dino was actually quite efficient. They managed to get 76.1% on that ImageNet linear benchmark using just 2 servers, each with 8 GPUs, running for about 3 days.
3 days? That's surprisingly fast compared to some training regimes.
Yeah, it actually beat comparable convent-based systems in terms of accuracy while needing quite a bit less compute.
Okay, that's a big practical plus. Makes it more accessible. Now, you mentioned something really interesting earlier about what the features learn implicitly, about scene layout and objects.
Yes, this is one of the most fascinating parts. They found that the features learned by DIA, particularly in the VTs, explicitly capture things like the overall scene layout and even the boundaries of objects.
Without being trained to do segmentation.
Exactly. This information just emerges.
Yeah.
And you can see it in the self-attention maps within the network.
Attention maps. That's where the model decides which parts of the image are important.
Right. And they showed these visualizations, figures 3 and 4 in the paper. They're quite striking. Different attention heads in the Dino VT would automatically focus on different semantic parts of the image. Like one head might focus on the main object, another on the background, even if the object was partly hidden or small.
Whoa. So it learns to separate things out on its own. How did it compare to supervised models?
The Dino models were much better at picking out individual objects in cluttered scenes compared to supervised VTs trained on the same data but with labels.
So the self-supervised approach led to a better grasp of object boundaries in complex situations. Did they measure that somehow?
They did. They used a metric called Jacquard similarity on a dataset called Pascal VOC12. They compared the segmentations derived from the attention maps to human labels.
And Dino did better.
Significantly better.
Yeah.
It showed a much stronger grasp of where objects began and ended, all learned implicitly.
That's incredible visual intelligence just emerging. And what about those patch sizes? They confirmed smaller was better.
Yep. Figure 5 in the paper dives into that. It clearly shows the KNN performance improving as you use smaller patches like the 8x8 ones. The features just get richer.
Okay. And I assume they did ablation studies, taking parts out to see what really mattered.
Oh, yeah. Table 7 goes through that. It confirmed that things like the momentum encoder and that multi-crop augmentation were really critical for getting those top results, both for KNN and the linear evaluation.
And the centering and sharpening, were they definitely needed to stop that collapse problem?
Absolutely. Figure 7 visualizes it nicely. It shows how, without them, the model's outputs can just flatten out, become meaningless. Centering and sharpening keep the representations diverse and useful.
Fascinating how these subtle design choices make such a difference. Did the projection head design matter much? The bit that processes the features before the loss?
Figure 9 looked into that. They found adding an L2 normalization step, sort of like a bottleneck, helps stabilize training, especially if the projection head was deeper.
Okay, another subtle point for stability. Did they play with the ViT architecture itself, like the number of attention heads?
A little bit. They noted that adding more heads to the smaller ViT model gave a tiny performance boost, but it also slowed things down slightly.
Right, the classic speed versus accuracy trade-off.
Yeah.
And figure 11, that TSNE plot, what did that show?
That was really cool. It visualizes the ImageNet classes based on the dino features. You could clearly see clusters forming, like all the different dog breeds would group together, different types of birds nearby.
So it learned semantic similarity, grouping concepts without labels.
Exactly. It built its own kind of visual taxonomy just by looking at the unlabeled images. Really powerful stuff.
Okay, Dino sets a strong foundation. Now, Dino V. This is the sequel, right? Bigger, better.
Pretty much. Dino V2 takes the core ideas of Dino but scales everything up. More data, bigger models.
Or how much more data, and where did they get it from without labels?
That was a major part of Dino V2, creating a new data set called LVD142M. Massive, 142 million images.
Wow, how did they curate that? Super cleverly. They started with a bunch of existing curated data sets, like ImageNet, Google Landmarks, etc. Then they searched through huge, uncurated web-scale datasets to find images that were visually similar to the ones in the curated sets.
Using image similarity itself to guide the curation, not text or metadata.
Exactly. Purely visual similarity. Then they did a lot of work to remove duplicates, ensuring the final dataset was diverse and high quality. Table 15 breaks down where the data came from, and Figure 3 shows the whole pipeline. It's quite sophisticated.
Okay, massive, carefully curated, unlabeled dataset. Did they just run the original Dino training on it?
They tweaked the training recipe, they kept the good bits from Dino, but also brought in ideas from other methods like IBOT, use the centering from SWI-V, and added a new regularization technique called Coleo to help spread the features out.
So an evolution, incorporating lessons learned. Table 1 shows how these changes helped.
Yeah, they did an ablation study showing the impact of each modification. It was a refined process built on Dino's success.
And the payoff. How much better was Dino 2? Significantly better, across the board, really. Figure 2 gives a great overview: image classification, object detection, semantic segmentation, instance retrieval, even depth estimation.
So improvements on lots of different vision tasks.
Huge improvements, often matching or even beating methods that use some form of weak supervision, like image-level tags.
Wow. Beating weakly supervised methods with pure self-supervision at scale. That's a big statement. What about on ImageNet again, the linear probe?
Crushed it. Table 4 shows DynaV2 setting a new state-of-the-art for self-supervised linear evaluation on ImageNet 1K by a large margin. And importantly, it generalized much better to tougher variants like ImageNet Real and ImageNet V2.
Better generalization? That suggests it's learning more robust features, right? Less brittle.
Exactly. And that really showed up in the domain generalization tests. Table 6 shows massive improvements on datasets like ImageNet A-R and Sketch, which have different styles or corruptions. DynaV2 is much more robust than previous SSL methods.
That robustness is critical for real-world use. Did it handle fine-grained tasks well, like telling different bird species apart?
Yep, strong results on fine-grained classification in Table 8, and also on instance-level recognition, distinguishing specific landmarks or objects shown in Table 9.
Okay, so it's got breadth and depth in its understanding. You mentioned segmentation and depth earlier.
Yeah, the visuals in Figure 7 are really compelling. Using just a simple linear layer on top of the frozen Dino V2 features, they got amazing results for semantic segmentation on 80/20K and depth estimation on standard data sets like NYU and KTI.
Better than other big models in that setting.
Often better than even models like OpenCLP when just using a linear probe on the visual features for those specific tasks. And Figure 8 showed it generalized well out of distribution for depth and segmentation too.
It's like the features contain this really rich, versatile understanding of geometry and semantics.
It seems so. And another piece of evidence for that was the PCA analysis they did on the patch features. Figures 1 and 9 show this.
What did the PCA reveal?
It showed that DynFD naturally learns to separate foreground objects from the background. And even more interestingly, it seems to capture distinct parts of objects, like the wheels of a car, the head of an animal, without ever being explicitly told about object parts.
Unsupervised part discovery, just popping out of the learning process.
Seems like it. Just emerges from learning on this large, diverse data set. And the patch matching in Figure 10 was also wild.
Patch matching. How so?
The DynFD2 features could match semantically similar patches across totally different images and categories. Like it could see the similarity between an airplane wing and a bird wing, or match parts of a real car to parts of a drawing of a car. Really flexible semantic understanding.
That ability to find common ground across appearance is powerful. Did they touch on fairness or bias? Always a concern with big data sets.
They did. Tables 12 and 13 look into geographical fairness and potential associations with harmful labels. The results were encouraging compared to some other models, showing fewer strong biases, although, some issues remain. It's an ongoing challenge.
Good that they're looking at it. And the environmental cost. Training these huge models.
Table 14 gives an estimate. It's significant, no doubt, but they argued it was relatively efficient for learning purely visual features compared to some of the large multimodal models, if you only consider the vision part.
Right. Okay, so putting it all together, Dino and Dino V2, they really map out a path towards powerful AI vision that doesn't need humans hand-labeling everything.
That's the core takeaway, yes. It's a shift towards AI learning to see from the structure of the visual world itself. The aha moment is that understanding emerges implicitly.
And for you, the listener wanting to get up to speed quickly, this represents a huge leap in how efficiently AI can learn to understand images, a real acceleration.
Absolutely. And the potential applications, they're just vast. Better object recognition everywhere, smarter autonomous systems that understand scenes more deeply.
Making powerful AI vision accessible even if you don't have Google-scale resources for labeling.
Exactly. And tapping into the trillions of unlabeled images and videos out there already.
It really does open up a lot of doors. So, okay, to wrap up this deep dive, here's something to chew on.
Go for it.
If AI can learn to see this well, pulling structure and meaning out of raw pixels without explicit guidance, what else could emerge as we keep scaling these self-supervised approaches? Are there limits?
That's the big question, isn't it? What other complex understandings might just bubble up? It makes you think about what learning really is and what it means for AI to interpret our world on its own terms. What does that unlock, and what new questions does it raise for all of us? Something to definitely ponder.